Welcome everybody to the wonderful Linear Logic first hilarious intro. Dang it, it's getting worse every time. I need a song. Talk to you later. Bye-bye. Oh boy, I'm sorry. I'm
Awesome.
really
That's
sorry.
great. And so here's the paper by Benedict Arens, Paolo Capriotti, and Regis Padotti on non-well-founded trees in homotopy type theory, if y'all are interested.
Nice. I'm definitely interested, but I have quite a bit of papers that I intend to read, so it will go in the queue.
That's good.
Same. I have no clue about homotopy type theory, so.
You went to a homotopy type theory
We did.
conference with me. Come on.
Oh, yeah, but I don't like that much. I got the book though, so it's right here.
That's awesome.
So I started the recording just to announce that I am woefully unprepared. Once again, I'm sorry, Jack, I have an analogous situation to you where it's like a transition from one thing to another thing and taking up a lot of time. And unfortunately, I'm kind of the opposite in terms of prioritizing a little bit game theory. But I want to do both. They're both top of my mind. So
Cool. So yeah, let's hear Martin talk for an hour then.
Great. So, yeah.
I have two things. I have to go in like 2 minutes. So small announcements. We may start next week. The Isabel study group. So everybody free to come. Jack will definitely start, and yeah, Carl and Martin, you're free to come.
awesome.
It will be held on Thursday.
Cool. Do you want to? What would you say is like a good little pitch for why you're interested and why you're starting the study group?
Well, so Isabel is one of the practical theorem provers out there, which is not only used in theory but also in practice. And also there is an EVM implementation in Isabel, which is now getting formalized with Hort triples, so you can prove the correctness of EVM programs. There's that. What else? It's.
I mean, that's pretty compelling.
Yeah, that's really cool.
It's pretty, and it's Hall, so it's higher order logic with types, so you can really write compact proofs in there. What else?
The EVM stuff, is the EVM stuff going to change when we go to like EWASM? Or is it going to be easy to...
Well, if we go into WASM, then we still use Solidity to compile contracts or to write contracts, right? And contracts written in Solidity will still compile down to bytecode or opcode, and this opcode will further down be compiled into WASM. So we can still use this middle layer. We're then free to go and use something else to compile to WASM, but we still can go this route down to opcode via Solidity and stuff. So it won't be obsolete as a whole, but there will be different ways to write proven programs.
But going through EVM bytecodes to WASM sounds a bit inefficient. I mean, it's not going to be obsolete, just not as good.
True.
Yeah, but it's something that you're going to have to write with the old contracts.
Yeah.
So at least it will exist, but probably something else as well that compiles directly to WASM.
Yeah, I mean, at some point, a WASM implementation in Isabel probably makes sense, but that's kind of further down the road.
Yeah, and that would be nice in general as well, because then you could all sorts of things.
Well, Isabel compiles down right now to ML, and if I'm not wrong, then there is already an ML to WASM transpiler, so we can use this.
Mm.
Yeah, and actually Isabel is one of those program proof things which pitch both at the same time. So you program in Isabel and then you write proofs about your programs in Isabel as well, and use this to prove the correctness of your programs. And those programs can be compiled further down into standalone programs, which is kind of nice. It's not a pure tier improver. It's not a pure programming environment, but it's kind of like mishmash of all practical tools. Yeah, which is nice.
Yeah, that's super cool. And you're going to be focusing both on like the Isabel, just how it works, like the theoretical foundations of Isabel, or both that and the like implementation of like writing Isabel smart contracts, for instance, proven smart contracts.
First, not smart contracts. There is one really good introduction book called Concrete Semantics. We will mostly reading it through until we get a fairly comprehensive level to get into the EVM implementation of Isabel in Isabel, and then, well, the goal is still to write proven programs, right? So push this further down, but it's not a strict schedule. So
cool.
Martin, will you join as well?
Maybe. Have you thought of a time yet?
Thursdays at some time, so make a suggestion.
Yeah, I don't know. I think I might not join actually.
Oh, too bad.
Yeah.
Because Martin has like a ton of Isabel experience already.
I know, but I'm not the biggest fan of Isabel, actually.
Why?
Because it's higher order logic and not type theory, and I think the proof tactics are sort of opaque, and yeah, it hasn't really spoken to me, and yeah, I think those are the reasons mainly.
I'm curious, what would you prefer?
As a theorem proving language?
Sorry, yeah, exactly.
So Agda is the one that I've had most experience with, and I would choose Agda, Kok, or Lean.
Right. Yeah, there was actually a question in the Ethereum formal methods getter to Yoichi, however, it's called Yoichi, right? Someone asked why he didn't use Kok instead. And he said that he had 4 years experience with Kok and like 4 months experience with Isabel, and the proofs were like 10 times smaller in Isabel.
Yeah, I talked to him about that also, and I think that my interests in theorem proving might be different also than what he is doing or what you guys want to do. So
right.
I'm not saying that Isabel isn't the right choice for that particular quest.
Cool.
Like Isabel is more practical, but you're thinking more theoretical?
Maybe, more or less.
There's actually a book currently being written. It's called Programming in Lean, which is fairly nice. It's doing like the same thing as Isabel does.
Yeah.
In Lean.
Yeah, Lean would be cool to learn, but I should probably learn the like homotopy type theory first.
Well, I mean, you don't have to do homotopy type theory in Lean. You can just do dependent type theory if you want to.
Okay.
You can just turn the univalence axiom on or off. It doesn't matter.
Nice.
Yeah, so I haven't.
So goodbye then.
Oh,
Sorry.
bye then.
All right. See you, Dennis. Thank you for coming. And I'll see you in the Isabel.
I have an ask, which is related to my thesis, but it's in linear logic and linear dependent logic, or linear dependent type theory specifically. And that is, if you guys can think of a nice type or a construction that is dependent on a linear term, then that would be nice. As a little background, in trying to integrate these linear independent types, the ways that people have been doing it mostly, as I think I said before, is that they allow type dependency only on intuitionistic terms, because it's sort of complicated to allow it to depend on linear terms, because then you need to account for how many times a variable has occurred in the type formation, and maybe if you want to use that same variable in the term formation, then you're violating linearity, and then you have a problem. But it turns out that in trying to do what I am trying to do, which is have a linear dependent type theory which is intensional, meaning that the type of equalities that you have, the judgmental equality, the equality that you can always check. I mean, not the type of equality that you can hypothesize, for example, is forced. The judgmental equality is forced on the type theory in the cases that I have seen, which has some disgusting properties, such as type checking being undecidable, and you're not being able to do homotopy type theory within this theory. So normally what you have in dependent type theory is two notions of equality. So you have the judgmental equality, which is something external to your theory, and then you have propositional equality, which is something internal to your theory, there, where you can assume, for example, that two terms are equal, and then that hypothesis will be a term of the type of identities between these two terms that you assume were identical. And so in trying to and so this is the difference between intensional and extensional type theories, where extensional type theories, you force some judgmental equalities to hold, but that in turn makes the type checking undecidable, and intensional type theory, where these identities or equations that you want to hold only hold propositionally, and so prove that they hold rather than holding automatically from your type formation rules. And so in order to really show that a linear dependent type theory, or to construct a linear dependent type theory which is intentional as one would like it to be, then one needs to have dependent elimination rules. So maybe I should now start sharing my screen. But you should also ask questions, because I feel like I said many things now. So questions.
So like when you say what was different, like intensional is propositional and extensional is judgmental, right?
Yes.
And why, like, do you have an example of a extensional type theory? Because I think I know what an intensional one is. Like, for example, the like regular dependent type theory.
Well, you can have regular dependent type theory, which is intensional and extensional, but I can show you specifically the point at which Vakar's linear dependent type theory becomes extensional. If I can just find the paper. Wow.
Math and music.
Yeah.
I'll be back in like 1.5 minutes.
Okay.
So what were the two types again? Intentional and extensional, you said?
Yeah. And so I actually want to show you maybe two papers. Okay, so this one. Are you seeing my screen right now?
Yeah, the whole screen. I'm seeing the paper.
Nice. So this is the identity type. So in a non-linear dependent setting, as long as you have a term of type sigma and another term of type sigma, you can form the type of identities between M and M. And the only way to construct a term of that type is to use this formal notion of reflexivity. You can always formulate that two terms are equal. Like this can be thought of as a hypothesis, or just the proposition M and N are equal. But in order to actually show that you have an inhabitant of this type, in other words, that the proposition is true, the only way that you can show it is by letting M and M be literally the same thing, and then saying that of course M is equal to itself.
Yeah, and how do you where is it saying that M and N are actually the same thing?
In the IDI here, it's saying that to construct an element or a term of this type, you can only do it from, you can only construct refl M. And since that is a term of the identity between M and M, so M, that is the same letter twice, you're saying that is a proof of M being equal to itself.
Yeah, M is equal to itself, which makes sense. Yeah. But the thing that I'm failing to grasp, which is probably a syntactic thing, is where N is said to be N, said to be M. So M and M are equal, identity, or is it reflexive? Is that the right
You usually call this term just reflexivity or refl. But so you should think of these two type formation rules as appearing in different contexts. I mean, not context in the literal sense, but like if you want to formulate the type, then you need this. And if you ever have just a term, then you can inhabit this specific type.
Okay, that makes sense. I see.
Yeah.
Yeah.
So as an example of an intensional type theory, here you have, for example, the dependent sum, which just looks like a pair. Like when you have, you can forget about the dependency here. It's not important, but just think of a pair of two terms, M and N. And now, using all of these rules, it becomes provable that all elements of the product type are actually on the form, the first projection of the product type, comma, the second projection of the product type, which is kind of tautological, but it really gives you a uniqueness of the inhabitants of the product type. So all products consist of pairs. That is essentially what you're able to prove with the identity type. But you can only prove it as a propositional equality. You can only inhabit a type of the identity between two pairs. So what you would say is that for any pair, this pair will be equal to the first projection of the pair, comma, the second projection of the pair. Like if I were to write that down, it looks like this. Maybe I can get a whiteboard somewhere. And there we are. Annotate. Okay, good. So I'm going to write over these.
Sing the song.
So what you'll be able to prove is essentially this. If you have an inhabitant W of a sigma type.
What's a sigma type?
It's a dependent product type. So it's a pair where the second component might depend on the first.
And that's what you showed in the second thing that you're showing after the identity.
Yeah.
We're showing the proof of, or the formulation of the sigma type.
Yeah, the formulation of it. Exactly.
Formulation, okay.
So
B is the second component of the pair, or the type of the second component, and X is the first component, and A is its type, right? Cool.
Yeah. So what becomes provable is the following propositional equality, that if you take the first projection of W like that in a pair with the second projection of W, then those are the same.
Mm-hmm. And I mean, this makes sense. Why was it provable propositionally?
Because of the way that the elimination rule looks for the sigma type. So the row type here is going to be our identity type. And if we can prove the row type with X and Y individually, then we can prove it for a pair of the dependent pair. So we can like deconstruct pairs in this way. And the computation rules tells us how that corresponds to just substituting the components of the product individually. And this, by the way, is judgmental equality. So usually to differentiate between the two, you can specify the type underneath. Like here, we would have an equality in a sigma type with X over A and B. When you're doing type theory, you get a lot of subscripts, like especially if you do big dependencies, then you have like a product type over a dependent type, and it becomes like you're almost writing horizontally, or I mean vertically. Okay, so in this particular case, in the type theory that is described in this beautiful paper by Hoffman, he describes, the syntax and semantics of dependent type. I can recommend this paper. He describes an intentional dependent type theory. But in the other paper that I've been reading, here it is, which is Vakar's paper of syntax and semantics of linear dependent types. If we look at the corresponding sigma type, which is given here. We see that he has the introduction, well, he has the formation rule, the introduction rule, and the elimination rule, and the computational rule, just as we had before. But
so, sorry,
yeah.
question. What's formation rule?
Formation rule is telling you when a type is well formed.
And which one is that?
Right.
It's the first one here. It says that if B is a type in the context of X, well, if you have a term of the type X in the context of the type A in the context, then B is a type. And so then you have B as a type which is dependent over A, and then you can form the dependent pair of B over A. It's just saying that this is a well-formed type. And to actually inhabit it, you must provide both an element of A and an element of B, where you have exchanged the variable X for A in the type of B. So then you can form this pair.
And what's the difference between the computation rules and the elimination rules?
The computation rule is saying what the elimination rule means on canonical elements of the type. So notice in the elimination rule here, we have a t, just like we should think of it as a variable, and we don't know really what it is. But if we have t as a canonical inhabitant of the sigma type, which is a pair, then it is exactly the same as if you were to have done the substitutions on X and Y individually.
So like in the elimination rule, T could be like a computation that will return a pair, but in the computation rule, we know that it will be a pair. Is that the difference? Or
yeah, that's sort of a way to look at it, yeah.
And what is the context? Sorry, finish your thought.
Mm-hmm. No, you go ahead, Carl.
I was just going to ask a much more basic question, just for the computation rule.
Yeah.
What is the is this similar to expressing computation? The thing we did expressing computation with within linear logic semantics? Is that like what defines the computation rule? Computation rules in general, I should say.
So I guess a slightly easier example would be lambda abstraction. So what lambda abstraction, like the application of a lambda term is essentially a substitution. So if you have lambda x dot f of x, let's see if I can write here maybe. Like if you have the following expression, well, why is everything capitalized? Okay, so in like simple lambda calculus, where you only have simple types, and maybe just give me a new page here. Okay, so in an expression like this is just a function. I mean, usually you don't write out the dependency on x here because it's assumed to be like that anytime you have a function like this. And so if you were to apply this function to an argument, say y, then this is going to reduce to when you, this is, what is it, eta reduction. It's going to be F, where you have exchanged all of the occurrences of X with Y. So this is like the computational rule for the product type. And actually, we have it here as well. If you have lambda B and then A, and you apply, well, if you have lambda B, where X is the variable of B, and you apply A to it, then you're just going to exchange all occurrences of X with A.
Okay.
So that's how it corresponds to computation, because it's just telling you how to rewrite an expression, basically.
Rewrite as an expression. Okay. Yeah. So essentially, you would have the formulation as a, when you say rewrite as an expression, basically that's, you would have it as like this implies that, but then you can instead use a more compact like syntax. I think I'm totally going cray-cray.
So, if you were to execute this, you wouldn't, like, this wouldn't be an implication. This would be like the output of your program if this is your input.
Yeah.
So that's why we should really think of it as a computational rule.
Okay, I see. Okay,
we are rewriting one expression into another.
Yeah.
I see. Okay.
But we can't really do that immediately because we want to be able to talk about variables. Maybe somebody could say something smart here about lazy versus eager evaluation. But the point is that when we define the elimination rule, we just think of the inhabitants of the sigma type as a variable, an arbitrary variable. But of course, we know that the only way to construct an inhabitant of the sigma type is by forming a pair like this. And so then the computational rule tells us exactly how this expression that we got from the elimination rule acts on canonical components of the sigma type.
Yeah, that makes sense. What's the U rule?
The U rule is the uniqueness rule, and this is the culprit here because it is what makes extensional. So this rule is saying exactly that that if you have a canonical pair and let's see, this TV. Yeah, so this is essentially some minor details. The judgmental version of the rule that I wrote down here, I don't think it's still here. Yeah, cool. So this expression here says that all elements of the sigma types look as the canonical elements. And this is essentially what this rule is saying also. It's saying that the inhabitants of the sigma rules, or the sigma type, is exactly the canonical inhabitants. And the point here is that this is forced as a judgmental equality, but this makes the type system undecidable and doesn't really allow us to do homotopy type theory.
I'm not sure if I follow. So the triple bar is judgmental equality.
Yeah.
And what exactly we're saying? So we're saying that T should be X and Y, we want to decompose T to X and Y in the judgmental equality of asserting that X tends to Y is equal to T?
No, so we should first look at the assumption. So,
Okay.
like our C type here is going to be exactly the sigma type, and so basically we just in like we're coming from here, and then we're forming this expression where C actually is the same thing as X tensor Y, and capital C is the sigma type. So
why is X tends to Y and Z the same thing?
So let's see if I have some colors. So this corresponds to this. Why didn't that get any color? Come on. Right, like this.
Oh, okay. But
So
like I'm not sure if I get it, because maybe I'm approaching this the wrong way. But when I only look at the elimination rule, then I don't see anything indicating that C has to be X tensor Y, and I don't see anything indicating that C, like big C, has to be the sigma type.
no, it doesn't have to. This is just the case where it is.
Oh, okay, right.
And in the case where it is, it's telling us that if we let the elimination rule act, like if we deconstruct the sigma type in this way, which I mean, this should really be thought of as a deconstruction of the sigma type, because instead of using X tensor Y here in the assumption, we're using X and Y individually, and we can get a C from that.
Yeah.
And so
and that's also why we do the let.
Yeah. And so in the case where we are trying to construct this particular element, which we should think of as a canonical element, then the uniqueness rule is saying that this is exactly the same as what we started with.
Yeah. But we're saying that we're saying that the judgmental equality is a term of the sigma type.
No, well, I mean, yeah, so that is a bit ambiguous syntax. So the judgmental equality doesn't have a type because it is an external construct.
Exactly.
But we compare two terms in the type of the sigma type. So it's a bit misleading, but like when we look at what the judgmental equality looks like, that's the way we write it down here. Well, let's actually go to term. Yeah, we write it down like this. But I mean, we could have just as well forgotten about the type here, because what's crucial is that the judgmental equality is not at all a type. It is a judgment. Mm-hmm. And judgments are external to the type theory, so it's something that will be done by type checking, and not.
Which you can't do.
So if you have this uniqueness rule, then type checking is undecidable.
Right. So what's the actual term that we're constructing there in the conclusion?
We're not constructing a term.
Okay.
We're saying that two terms are judgmentally equal.
Right. I see.
And that makes them undecidable.
Yeah, I'm not sure. how that proof goes, that the type checking becomes undecidable when you force this requirement. But I mean, you want judgments to be something decidable, because judgments are like the external things that you want to require, like it's like requiring that every question is well posed. I mean, you want to be able to decide whether a question is well formed or not before you even begin to answer it. And that is sort of how we should think about judgments.
The judgment are what you would actually implement if you would implement this as a type system.
Mm-hmm. Yeah. Yeah.
Yeah, okay. I understand those 4 rules now.
Yeah, so, yeah, Carl, question?
Well, my question was actually, I realized that there was like a conceptual thing that I've always kind of somehow scooted around and never fully understood, that I was going to ask. But if you have, please finish your thought, because it's totally separate.
No, you can go ahead, ask.
Okay, so my question is my time. So the real thing is, when we were talking about the expression, I clearly have some kind of confusion. So the lolly, I just drew a very nice lolly here. In linear logic, I'm going to linear logic right here. That is, how does it relate to like something like, oh god, this is going to show my just disgusting ununderstanding. Early in the lectures in linear logic, right? We showed that we can get to the we showed the Lolli formulation. I'm pretty sure it's Lolli, it's not turnstile. Is similar, is like a more is a different way to write something like this. First, is that correct? And what is the difference between it? Is it just a more convenient syntax so you can nest these implications? Are my words correct or incorrect?
Yeah, I mean, I think it's a good question.
It's a very good question. So I would say that this is, Martin might disagree and feel free to explain why. I would say that this is intentional and this is extensional, in the sense that this is like outside of the logic or the type theory, while this is inside of the logic or type theory.
Yeah, that is a good way of expressing it, I think. I think of A Lolli B as a way to
Interesting thing is that arbitrary propositions, sorry, it doesn't even have to be Lolli, but you can take tensor or Lolli or width or whatever and go from those propositions to rules to that look kind of like these, all with a little bit more context, like deltas and stuff.
I actually dropped out. Do you know when I dropped out, or did you not notice? I apologize.
Not exactly.
Okay,
do you know when you dropped out?
I do know. I dropped out before you started drawing on the screen outside of the thing around the A Lolli B and A over B. I think my internet just like completely, I had to reconnect.
So did you hear when I
External
talked
and
about
internal to the type theory, to the linear.
right, and then Martin's, and then you had heard Martin's
That's,
explanation, but not the rest.
yeah, I think so.
Okay. So once you get to the lectures on focusing in the linear logic course, you will actually see how you can go from these propositions like that are intentional to the logic to these kinds of inference rules. Only they will be derived rules. So there will be really be like a dashed, oh, that's not a dash, like a dashed line saying that you can go from something to something that look more or less like this, only with more context and a little bit more general. So they really do have a close relationship to each other. But this allows us to be a little bit more expressive because it contains context and other stuff. And also, like, you can build your reasoning as propositions within the logic instead of as inference rules about the logic.
Okay, I see. So you can build, when you say, so you are able to then, instead of just inferring things about the logic, you can say that last sentence again, build inference rules within the logic.
Yeah, more or less, yes. So you can,
Like
I think that's a good characterization, actually.
like in your formulation of a in your formulation, you can include inference rules, versus in the other circumstance you would just be expressing inference.
Yeah, so this horizontal line just tells you how you go from one true thing to another true thing. And while what's
that, Martin?
And like, while that is useful, it isn't like only building things by saying, yeah, like only expressing things by jumping from truth to truth isn't like expressive enough. It's good to have like truths that are dependent on some context and so on.
Yes, exactly.
And that's when we start to need propositions instead of just simple jumping from the truth to truths.
Cool.
Hopefully that kind of makes sense.
No, I think it really does, and it definitely clarifies that, because I've always, every time I write Lolli, I'm like, I really don't understand you fully, and it's been like bugging me. Yeah.
I feel like one of the goals of logic, or heuristics maybe, is to try to abolish meta logic, in the sense that you want all of the logic that you actually want to do internal to your theory, and you don't want to step outside of it and like talk about how the rules actually work, because then that's just gonna lead into infinite regress. So when you have Lolli, you're sort of parametrizing the type of rules that are on that sense.
So you avoid the recursive.
Yeah, you're able to talk about things internal to your theory.
Cool.
Just nice. You do Lolli instead of.
Exactly. And another example that could be more clarifying is the tensor, because if you have if you know that A and B are true separately, then you can conclude that a tensor, that's the world's smallest tensor, then you can conclude that a tensor B is true, So now I'm kind of mixing here.
What rule is
Honestly,
that?
Sorry?
Or is that a rule, or is that just a just like?
No, I'm just kind of talking in between. I'm not sure if this is gonna end up well. It doesn't, like, this rule doesn't exist. It's a simplified version of tensor right.
Okay, I see.
Yeah.
It could have been the and introduction in propositional classical logic, though.
Yeah.
Cool. Yeah.
No. Okay. No, I am actually starting to realize that this won't really make sense. So forget this.
That's okay.
Okay.
But this is super useful, and I also have to say that, like, starting from just linear logic, it's like I'm trying. Well, here's another random question. I don't know what you guys are on time. Like, if you have to leave.
I need to leave in like 7 minutes.
Okay, so maybe in a short, like, dependent types. Linear, like, dependent types is the large kind of, how does what is the alternative to dependent types? Maybe independent types.
Well, I mean, simple types is usually the less advanced version of dependent types.
Okay, so a lot of and linear logic versus, and so yeah, dependent types is, linear logic isn't directly related to dependent types, right?
No,
That's true.
Okay.
they are very different, and people, including Martin, are trying to combine them, but so far no one has been successful. That's the black hole we talked about earlier.
I see. Okay. So dependent types are like a field of type theory, which expands on, allows you to formulate types and build them and construct, really interesting types. And then linear logic is a subfield of the logics, which allows you to express finite resources and the transformations between those resources. Is that like a general moderate?
Yeah.
Okay.
Yeah.
Pretty much.
Cool.
So if I can just get to my final point that I would like to make, which is my ask, then the point is, in order to like make the type theory intentional, that we would all like to, then I've tried formulating some different rules. But the point is that you really can't get away, I think, from having your types be dependent on linear terms. And so I would like to ask you guys for examples of such types, like, because it seems like when I was trying to think of them, I thought of scenarios that sounded like smart contracts. So Krishnaswamy's paper talks about a linear dependent type, which is dependent on a intuitionistic term, which is like tuples of length n, like a tensor, a tensor, a tensor, blah, 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 n times many tensors. That like n tuple is, if a is a linear type, then that is going to be a linear dependent type, but the term dependency is on an intuitionistic term, because natural numbers are not resources. So I'm trying to think of dependent types that depend on linear terms. And like, this is an example I wrote up today. Like, if we think of a store having a 3-for-1 or a 3-for-2 type of deal, where you can buy 3 caramels for $2, then I would expect this to be maybe a linear dependent type where the type dependency is actually on a linear term, because the tuples would make a difference for the output type. Like if you give $2, then you get 3 candies. If you only give $1, then you only get 1 candy. So it would depend on the tuple then, I think. And if this makes sense to you guys, then, and if you come up with any examples, then I would be happy to hear them. Because it's really hard to make sense of all of this. I mean, I've been writing down some rules, and I really have very little to go after when trying to figure out whether these rules are correct or not. It's just like, this makes sense, like syntactically, but what does it actually mean?
Yeah. Yeah, definitely. I will try to do that. I think
Nice.
I have some ideas forming from a conversation with Dennis last Friday, but I will have to write them down before I can say anything.
Nice. Very cool.
Awesome. Cool. Well, that was very helpful and interesting.
Yeah, thanks. Thank you guys for listening.
Thank you for presenting.
And next week, I'm not going to be in Paris, and I'm going to be also hopefully calmed down. So I guess I will have more substantial questions. Although I had a couple, which I'm happy about.
Yeah, very cool. Then I'll see you guys next week.
Yeah.
All right. See ya.
Or on Sunday.
Yeah.
Bye. Bye.